So let's continue our discussion of the Rice method with some different types of equilibrium problems. Let's look at this first example. At 700 Kelvin, we've got carbon monoxide reacting with water, and it's going to form carbon dioxide and hydrogen. So let's get that reaction written first. So we've got carbon monoxide plus water reacting to form carbon dioxide and hydrogen gas. So that's already balanced as written, so we're good there. It says that the equilibrium constant for the reaction is 5.10. And it's talking about this in terms of moles and liters. So we're going to say that Kc then, our concentration equilibrium constant, is 5.10. So we have an experiment in which 0.5 moles of carbon monoxide and 0.5 moles of water vapor are mixed together in a 0.5 liter flask. There's a different number other than a 1 liter flask, so we're going to have to do a calculation. Calculate the concentrations of all species at equilibrium. So our first little side equation is going to be to convert that 0.500 moles per 0.500 liter flask into molarity, and it's going to be just 1.00 molar for each one of these. So I know that I'm starting with 1.00 molar carbon monoxide and 1.00 molar H2O, it says. So carbon monoxide and water, we have the concentrations. And we have no carbon dioxide or hydrogen gas. So that takes care of our reaction and our initial concentration. We need our change and our equilibrium values in order to do this calculation. So since this is a one-to-one reaction all the way through, we're going to be losing carbon monoxide and water. At the same time, we're gaining CO2 and hydrogen. So our equilibrium values are going to be 1.00 minus x, 1.00 minus x, x, and x. So let's go on and write our equilibrium expression. We know that Kc is going to be equal to CO2 times H2 over CO times H2O. So there's our equilibrium expression. We know that Kc, we already established that it was 5.10. And both our CO2 and H2 are x, and both our CO and H2O are 1.00 minus x. So what does that translate as? It translates as this, x squared over 1.00 minus x squared, which is x over 1.00 minus x quantity squared. Now, what does that mean? Okay, now we've used this before, and we've looked at problems where we knew that if we have a value on top of a fraction that's squared and a value on bottom of the fraction that's squared, the quantity then is squared. That's rules of squares and square roots. So what we have here is a perfect square. Now, yes, we have learned that we can neglect x, but guys, the only time you can neglect x is when you have no other option, rather than to do that or use a quadratic equation. This time we have an option. All we have to do is take the square root of both of these values, and we'll end up with a relatively easy problem to solve. So once I have this, taking the square root of 5.10, I get 2.26 for my value for the square root of 5.10. And of course, if I take the square root of something that's squared, it's going to be x over 1.00 minus x. So I'm going to multiply both sides by this quantity. And what I end up with is 1.00 minus x times the 2.26 is equal to x. Distributing that, I get that 2.26 minus 2.26x is equal to x. And now combining terms, I get that 2.26. I'm going to add 2.26x to both sides, so I end up with 3.26x on the right-hand side and an x value of 0.693. So there's my x value. Once I have x, I'm looking pretty good because all of my equilibrium concentrations that it wants me to find are in terms of x. So both CO2 and H2 are x. So concentration of CO2 is equal to the concentration of H2, which are both equal to x, which is 0.693 molar. My carbon monoxide is equal to my H2O. They're both the same, which is 1.00 minus x, and that value comes up to be 0.307 molar. So those are my concentrations of those substances. And we did not have to neglect x. Remember, you cannot neglect x if you have a perfect square, if you have a perfect cube, if both of them are raised to the fourth power, you might find something like that on your worksheet that's coming up for today. So watch for that. Okay, let's look at our next example. Our next example says that we've got solid ammonium carbamate and it's going to sublime and it dissociates completely into ammonia and carbon dioxide. And it says that at 25 degrees Celsius, we've got the pressure, the total pressure of the gases in equilibrium is 0.116 atmospheres. Total pressures of the gases in equilibrium is 0.116 atmospheres. What's the equilibrium constant? We haven't done one like this yet that asked us to find the equilibrium constant. So let's see how this plays out. We've got N2H6CO2, it's solid, reacting, subliming to form, or it's just when it sublimes, it dissociates in that process. So it forms NH3 and CO2. Both of those are gases. Now, I'm emphasizing that because here's what I've got for a reaction. For my initial concentrations, both of these are 0, and here's the big, huge, important thing. We don't care what the initial concentration or anything is of N2H6CO2. Why? Because it's a solid. Will this show up anywhere in our equilibrium expression? No, it will not. So we don't even worry about putting any values down for it. We are going to put a change down for our NH3 and CO2. We're going to be adding 2x for NH3, and we're going to be adding x for CO2. So our equilibrium values are going to be 2x and x. 2x for NH3 and x for CO2. Okay, and again, we don't care what the ammonium carbamate is. So, okay, what does that do for us? We've got this 2x and this x, and we have what other value? Well, the only other value we know is that the total pressure of the gases is 0.116 atmospheres. What's the only thing we know about our two gases? That they are related to each other in these terms. Well, think about it. Remember, the total pressure of gases is equal to the pressure of each of the gases added up. So we can say that if we know that ammonia is 2x and we know that CO2 is x, then we know that the value, they are supposed to completely add up. according to Dalton's law of partial pressures, to 0.116 atmospheres. We only have one variable. We're going to be able to solve this. 3x is equal to 0.116 atmospheres. So x is going to be when I divide both sides by 3, 0.0387. So I know that the pressure of CO2, let me write that a little differently. I know that the pressure of CO2 is X. So the pressure of CO2 is 0.0387 atmospheres. And I know that the pressure of NH3 is 2x. So I know that's 2 times that value, so it's 0.0774 atmospheres. Well, once I know these guys, I'm home free, because look at what the rate expression, or excuse me, the equilibrium expression is going to be. Based on my equation here, the equilibrium expression is going to be that Kp, now we're dealing with pressures now, so it's Kp, not Kc. Kp is going to be the pressure, not the concentration, the pressure of NH3 squared times the pressure of CO2. N2H6CO2 is not involved, it's a solid, so we don't even need that in the equation. And since we know that the pressure of NH3 is 0.0774 atmospheres squared, and the pressure of CO2 is 0.0387 atmospheres, and I'm not sure why I'm putting atmospheres, because the units are not going to be involved in the final answer anyway, since it's an equilibrium constant. But I end up with an equilibrium constant of 2.32 times 10 to the negative fourth. Sorry, I couldn't find it. 2.32 times 10 to the negative fourth. So we just figured out the equilibrium constant for this Kp for this particular reaction. Okay, we've got one more problem to do. This is another Kp problem. This time we're dealing with the reaction N2O4. Both of these are gases, so they're both involved, so I'm not going to bother to put down what they are. N2O4 forming 2 NO2s. So that's our reaction. And we've got our rice to come up with. What do we know? It says that the equilibrium constant is 0.15, so Kp is 0.15. It tells us the pressure of N2O4 at equilibrium is 0.85 atmospheres. Be careful, don't put that down as initial. It said it was at equilibrium, so this is what we've got, 0.85 atmospheres. So we know what the equilibrium value is for N2O4. We know we started out with 0 of this, and we know that it's going to increase by 2x, so we know this is going to be 2x. So how do we set this up? We're going to make our equilibrium expression just like we always do. The fact that Kp is going to be equal to the pressure of NO2 squared over the pressure of N2O4. And we know that the pressure of NO2 is going, we know the values for, I'm not going to put that equal sign there. We know the values for both Kp, which is 0.15, and we know that the pressure of NO2 is our unknown, that's squared, over 0.85 for our pressure for our N2O4. So those values we know. So the only thing we've got as a variable is the pressure of NO2. And since we know the pressure of NO2, all we have to do is to multiply out our 0.15 and our 0.85, and we get that the pressure of NO2 squared, I didn't say that very good, but this is what you have to do, is going to be equal to 0.1275. And if I square root that, then I get that the pressure of NO2 is 0.357 atmospheres. Now be careful because that's not what it asked for. It's very easy to get an X value or get a final answer and not answer the actual question. So we found our pressure of NO2, that's 2x, that's our 2x value. Now, if it did not ask us any of this, but this would have been, this initial here, would have been some unknown value, and the change would have been minus x. So knowing that NO2 is 2x could have been important to us in another type of problem. Perhaps it might have asked us what the initial concentration of N2O4 was. It would be important for us to know what X was, because then we could simply add that to the 0.85 to find out what N2O4 was at the beginning. This particular problem doesn't ask you to find that, but you might have one like that on your worksheet, so watch for that. All this one asks us to do is to find the total pressure at the end. We now know the pressure of N2O4 at equilibrium is this, and we know the pressure of NO2 at equilibrium is this. So the total pressure is going to be equal to the pressure of N2O4 plus the pressure of NO2, which is going to be 0.85 atmospheres plus 0.357 atmospheres. And we end up with a value of, to really, 2 places past the decimal is really all we can support, 1.21 atmospheres for our total pressure.